So in question 7, we're asked to find general antiderivatives, and these are pretty quick because most of them are set up sort of like a polynomial. It's just addition or subtraction, and we're just going to be applying one rule at a time. There won't be any u substitution. So the first function is f of x equals, and we want the general antiderivative. So I'm going to call the antiderivative f of x, capital F of x, and the antiderivative of e to the x is e to the x because the derivative of e to the x is e to the x. The antiderivative of 1 over x is ln of x. And because it's a general antiderivative, I do have to account for the fact that there could be a constant at the end of that antiderivative. So that would be the answer to 7a. G of x is secant squared of 5x minus 3 times sine of x. So this one's slightly more complicated, but it's not too bad still. We know that the antiderivative of secant squared is tangent. So we'll start there. Tangent of 5x. Now think about the chain rule. When you apply the chain rule, if you were to take the derivative of tangent, so dx of tangent of 5x, that would be secant squared of 5x times 5. And you'll notice in the original function there is no 5, so we need to put something there to cancel out that 5, which is going to go there once we take the derivative of tangent of x. So what we're going to put there is a 1/5. Just like when we do the power rule and we account for those exponents coming down, we'll put a 1/5 tangent of 5x plus. And the reason it's plus is the antiderivative of sine is going to be negative cosine. So this sign is going to change. So 3 cosine of x. And again, there could be a constant. All right, the final letter C here in number 7. So big H of x is going to be the antiderivative of the square root of x. So when we do these, we should consider them to be fractional exponents. And so when I take the antiderivative there, I have to envision that going up by 1. So it is going to be an x to the 3/2. But because we don't see a 3/2 in front here, there's going to have to be a 2/3 in front to cancel out that 3/2. And if you're having a tough time figuring out how these things work, just try taking the derivative of this right now and watch what happens. And you'll see why it is we need that to be there, because you don't see a 2/3 in the original square root of x. Plus, this is going to have to be x to the 3rd. Do I need to put something here to cancel anything out? Nope, because the derivative has the 3 that we want. So that works out pretty nicely. And then this one is going to take a little bit of thinking. So when I go up 1, or increase that exponent by 1, it's going to have to be an x to the negative 4th. Okay? But when I take the derivative of this, I need there to be a 1/2 here. And it's a positive 1/2. So I'm going to need there to be a negative 1/8 there, so that when I do take the derivative, because the derivative of this would be negative 4 over negative 8 x to the negative 5th, and that would be 1/2 x to the negative 5th. So that's what we're looking for. So we're going to say minus 1/8 x to the negative 4th, and don't forget, plus c. In question 10, they're asking you to evaluate some integrals that are a little bit more complicated than we had in question 7. So we're going to be using some u substitutions in these cases. So the first one is an indefinite integral, and we're asking for the integral of x times the square root of 1 plus x squared dx. And so we're going to start off with letting u equal 1 plus x squared. And we're being strategic there. We're trying to identify a portion of this that is a composition of two functions, and I do see one here. There's a square root function, and inside of that I have a quadratic. So I'm going to use the interior of those two composed functions and let u equal that. I'm also recognizing that the derivative of that interior function contains the only other element of this integral. So that's going to be a good thing as well. So if u equals 1 plus x squared, then du equals 2x dx. The only component of this that we don't need is this 2, so I'm going to move that to the other side. 1/2 du is equal to x dx. And now I have all of the components that I needed. I have my x, I have dx, and I have 1 plus x squared. So now I can rewrite this as the integral of the square root of u, because I let u equal that interior function, du, and remember when I put that du there, that and the 1/2 represents all this stuff. So I can't just put the du, I also have to put the 1/2, which is a constant that I'm going to put outside the integral. And now I can evaluate this because I can take the antiderivative of the square root of u, so that's going to be 1/2 times u to the 3/2 times 2/3. We just did an example like that. Plus c. And if we want to here, we can do some things to make this look a little nicer. There's some cancellation that's going to happen here, so I'm just going to say that it is the square root of u cubed over 3 plus c. And so my final answer is going to be 1 plus x squared cubed. The square root of that quantity over 3. A lot of different ways that you could write this. All right, example B. Now it's a definite integral. We're going to actually get a value out of this when we're finished here. So when we consider how we're going to be doing our u substitution, we're looking for a place where we've got a composition going on. And I see a composition happening here. I see a sine squared, well, an x squared function, and then inside of that, a sine function. So the interior function is sine of x, and I'm going to let u equal sine of x, which is going to mean that du is equal to cosine of x dx. And actually, I should be careful here because we're not talking about x, we're talking about theta. All right. So this is going to take care of a lot of things. I've got a cosine of theta there, and I've got a d theta there. That's great news. And I've got a sine of theta there and there. So I've done a lot of good for myself here by making that u substitution. So let's go ahead and replace the components of the integral with our u substitution components. Now before I put the interval over which we're integrating here, I do need to make some adjustments based on that substitution that I made. So if u is sine of theta and theta equals 0, then u is equal to sine of 0. And what is sine of 0? Well, that's going to be 0. Okay, but what if theta is pi over 2? Well, then u is going to be equal to sine of pi over 2. So whatever sine of pi over 2 is, well, the y-coordinate of pi over 2 is 1, so u is equal to 1. So now I'm integrating from 0 to 1 of 3 u squared plus u du. And that's what I get once I've substituted all of my components. Okay, so now I can take the antiderivative of 3u squared plus u, and so that's going to be equal to u cubed plus 1/2 u squared, evaluated from 0 to 1, and now I can actually plug in these values. So I am going to have 1 cubed plus 1/2 times 1 squared minus 0 cubed plus 1/2 of 0 squared. This is all going to go to 0, so it really just matters what came out of here. That's just 1 plus 1/2, which is 3/2. Okay, and finally c. So c is a derivative of an integral. And we should remember the fundamental theorem of calculus part 1, which says that if f is continuous on a to b, then if you've got a function g of x that equals some integral from a to x of a function, then this function is continuous on a to b, it's differentiable on a to b, and g prime of x is going to equal f of x. And an important thing to note here, not f of t, f of x. So this is a very simple application here of the fundamental theorem of calculus part 1. We're just going to be able to say that because we are taking the derivative, as we did here with g of x, of a function, if we consider this to be your g of x, then this is going to be equal to sine of 3x to the fourth. Now remember, if we were to take the derivative of something that had a 3x inside of it, there would be a chain rule involved where we would have to multiply by the derivative of that interior function. So if you forget about this derivative component here and you imagine that you just took the integral of sine of t to the fourth from 3x to 1, you would take the antiderivative of this and you would plug in 3x minus, then you would plug in 1. Now the antiderivative of this of 1, that's all going to disappear when you take the derivative because that's going to be a constant. So that's not playing a role here. But once I take the derivative of that element that has the 3x, it's going to look exactly like this, but it's going to have to be multiplied by the derivative of 3x because of the chain rule. So I can't forget here that in this case, because that upper limit is a 3x and not just a 1x, I do have to multiply it by the derivative of 3x. And so we could make this look a little bit nicer here because 3x to the fourth could be rewritten as 81x to the fourth, and that is going to be our final answer.